the screen?
Yes.
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 So, well, shall we start?
Yes, that'd be great.
Okay, so please, you're free to interrupt me. Just remember that I don't hear you very well, so you maybe have to insist or to shout a bit. So the idea of the talk was to
François, could you do it full screen? Like click the full screen button for the talk?
yes, like that.
Yes, that's great. Thanks.
So the idea was that the talk would be lasting half an hour in principle.
Nobody wants to see.
Maybe a little longer, but you please tell me if you want me to speed up. So as well, so this is the title, which you know, nanocomposites at rest and under deformation. And you know most of my co-authors on this list, of course, so I will not comment it. I remind you that Bridgestone America was supporting the trip, so even if it was not perfectly successful, I thank them anyway. And so the idea will be that I discuss about the nanocomposite at rest and under stretching. And actually, I think that I have more to say about the stretching case, because the nanoparticle nanostructure at rest is, I think, now consensual. There have been so many achievements that I think people start to understand well. It has taken 15 years, but to understand well how you obtain the different kind of dispersion of a nanoparticle. And so here I will show some of our works in the idea that it's just in a way to show that they agree with the consensus, and then I will study them in the deformed case. Okay. So what we did some times ago is some very simple way of dispersing some nanoparticles. These nanoparticles were either naked or grafted, and in that case, the grafting was some grafting from with some initiator, which was first grafted on the silica, which is 10 nanometer diameter, and then the polymerization was starting from the surface, and whatever the silica was naked or grafted, we mixed it. We mixed it with a polymer in a solvent, which is dimethylacetamide, which has a high boiling point solvent, and we made the mixing evaporate for a very, very long time, and so we believe that this is the reason why we obtained some rather well-defined dispersion. So the dispersion, they have been first actually characterized by the scattering curve, so logarithm of the scattering versus logarithm of the scattering vector, both in X-ray in blue here and in neutron scattering in red, and both agreed together. So you can also, we also succeeded to do some electronic microscopy, and we could see a good agreement between the two, and we could see that in the non-grafted case we had some rather satisfying dispersion as some small clusters, okay, and meanwhile when graft the nanoparticles, we can vary between a well-dispersed case here, all the particles are individual, to a very phase-separated case, and through via some well-dispersed clusters. And this, we could see that the effect of that was controlled by the ratio between the degree of polymerization of the grafted chains and the degree of polymerization of the matrix chains. And you could see that if this ratio was large, the large chain of the matrix, the small chains of the matrix were able to swell the grafted chains so that the different silica particles were well separated. Meanwhile, when this ratio was very small, the chain matrix were very large and could not actually swell anymore the brush, and so could not prevent the nanoparticles to aggregate. And this effect could be summarized on this diagram, which is representing as a function of this ratio, this quantity, which was first introduced by Dejean, which is the product of the grafting density and the square root of the polymer of the grafted chains degree of polymerization. And all that has been nicely summarized in a paper by Kumar and other people, Dimitrovic, and also our student Nicolas Jouot. And you can see on this diagram the different case here which correspond to our sample, and all the other cases which have been collected by Kumar and Tan, and which show that actually you have different regions in this diagram, well dispersed, phase separated on the full right hand, and some connected cluster in this other part of the diagram. So, in a way, there is a consensus in the fact that you can put most of the systems on the same diagram. And also, Kumar et al., they showed, in a particular case, a nice correlation in between this dispersion and the stress versus strain curves, which are shown here, okay, on the left-hand side, where you see that at small strain, the reinforcement is much stronger when the systems are made of clusters compared to the case where it's phase separated. And this is the same as a function of the frequency. You see that some low frequency behavior appearing when the systems are in the form of clusters. And this reminds some very old work of us, actually Yaya Harbi and Kaban, where we could obtain also some dispersion in terms of using some mixture of latex polymer beads and nanoparticles of about the same size. And you can see here that we could obtain well-dispersed systems or very aggregated systems, depending on the pH. And that, in this case also, you could obtain very strong difference in the modulus in between the aggregated case, which was showing a very strong increase of modulus, compared to the basic case, which correspond to well-dispersed system where there is no reinforcement at all. This has been shown later on by Van Genix and Oberdisson on their studies of the same kind of latex nanoparticle composite. You can also look at all this for some industrial systems, which we, in our case, we did with Ch1. You can actually, in this case, you start from some aggregates. You don't start from individual particles, and you mix this aggregate with rubber in a stirrer, an industrial stirrer, and you both mix and break and reaggregate the aggregates, and the result of it is rather well dispersed, well characterized aggregate actually, which depends on the type of wrapping you put on this aggregate. So here, one other interesting thing is that you can actually characterize by scattering the different aggregates, which is not always very easy by electronic microscopy because industry uses some very concentrated system. So the way of actually the way of accounting for the shape of the
Tu sais, François, une fois que tu as préparé tes
is
trucs,
to build progressively the scattering, starting from the form factor of a single nanoparticle, and then adding some interactions in between the two particles. This modifies the scattering at low Q here. Then combining this with the shape, the form factor actually of an aggregate with a given fractal dimension, and finally reintroducing some interactions between two different aggregates so that we are left with this curve. And we have only now to add another contribution, which is observed at very low Q and which comes from very big clusters, which we assume not to be so important in the properties of a system, while it's not completely proven. Okay, so another way of accounting for this scattering is to do some reverse Monte Carlo modeling. That means you actually create some aggregates by Monte Carlo simulation, and you constantly readjust the result with comparison with actual measured scattering. Okay? And what we're saying, the people of Montpellier in their colleagues' review, is that in the future, probably the best way of representing those aggregates would be to combine such way with some more information from the electronic microscopy picture, to make a kind of combination of both. So this is about it for the structure under at rest. Now I would like to talk a bit about the structure under deformation. So I actually consider a piece of material which is stretched, uniaxially stretched, so by a factor an elongation ratio lambda, and at the same time, to keep the volume constant, you have some shrinking in the two other directions, lambda y and lambda x, so that okay, so this is the definition of deformation of the sample itself. So the very simplistic idea would be to say that your system is deformed affinely to this macroscopic deformation, which would mean that all the nanoparticles are deformed as some ellipsoids, and also the distance between the different nanoparticles are also deformed affinely to the macroscopic deformation. And this would lead to a scattering which is in shapes, which has the shapes of some ellipses, which are centered, of course, on the center of the beam. And if you now look at the scattering along different directions, you would see some scattering curves, which are identical to the isotropic one, but shifted by a factor log of lambda, or log of lambda x in x direction, log of lambda z in the z direction, etc. So so this would be the most simple case. Well, in practice, it's not the case because first, the nanoparticles are not deformed, and second, it is not sure that the distance between the nanoparticles would also be deformed affinely to the macroscopic deformation. So altogether, actually, what we obtain is really very different. This is this kind of shapes, which are made of two wings here. They used to be called butterflies some times ago, and you can first explain them by the fact that your different clusters here, they are moved together, but they not deformed. They are not deformed, but the distance between the center of mass is deformed. So if you first assume that these distances are deformed finely to the macroscopic deformation, you obtain this kind of shapes on the left hand on the top. Now, if you stretch more your sample, instead of getting 2 lobes, like as here, you get four lobes, okay? And in this case, you have to introduce an additional effect, which we attributed to the fact that when you shrink your sample in the transverse direction, the different clusters of particles are forced to hit together, and they must rearrange by sliding with respect to each other. And by doing that, we obtained this kind of 4 lobes simulated shapes here in the middle, and with Julian and Yaya Harvey. And later on, a Japanese group with Amemiya made some very nice simulation, much more precise, and obtained very similar scattering patterns in a very dedicated work. So a priori, it seems to be explained, the displacement of particles seems to be well accounted in the scattering, but in practice, I think there are still some many complications and many things to understand along this direction. And I will show you just two examples. Actually, one example in which the nanoparticle concentration is low, and you see here the scattering on 2 different directions on the left. Actually, this is not the scattering. This is the so-called stretcher factor, which represents the Fourier transform of the distances between the different clusters. And you see on the perpendicular direction, you can see here that the main information, which is the Q star corresponding to the abscissa of the pit here, which is the distance between particles, is actually not deformed so much, although we vary from deformation 1.5 to a large deformation of about 3. So this should be visible, and we see nothing. Meanwhile, on the parallel direction, so along the deformation, you see clearly some changes, and actually the shift of this pit in the structure factor is actually following a curve which is close to an affine deformation. So we have a contradiction in between the 2 different directions, which can be maybe little understood by the fact that you have some rotation on the different clusters. As you can see here on the right, this 10 micrograph has been made on some samples which have been first stretched and then microtoned. And you can see that there is a strong orientation of the different clusters. So this is one case, but if you now look at a more concentrated case for the same kind of particles, you see now that the pit abscissa, Q star, is now following the deformation in an affine way, both on a perpendicular direction and parallel one. So actually, going to higher deformation makes the displacement more refined, although in principle there is much more difficulty for different aggregates to rearrange with respect to each other. At the same time, the stress, the mechanical stress as a function of the elongation, is actually quite different in the different concentration for the different concentration values. When it's actually non-affine, you have a gentle increase of the stress. Meanwhile, in the high concentration case, you can see that the curve for the stress versus the elongation ratio is made of two parts, a strong increase, and then you have a kind of overshoot, and you see that you return to some much more moderated deformation. Sorry about that. So that finally, I want to discuss a little more this effect. Okay. First, so I return to this fact. Okay. But what I would like to show you is some deformation cycle. So here we can make a deformation cycle by stretching first in the first deformation. We obtain the same curve as the one I showed you before. Then the scattering is made of 4 lobes as I showed you before. Then we go back to the initial length, more or less, because the sample has difficulty to really recover its actual length, but there is no stress anymore. In this case, you see that you obtain scattering patterns, which is completely anisotropic, instead of the initial one, which was completely isotropic. So you have actually strongly rearranged all the clusters during first stretching and the recovering, and is obviously irreversible deformation. We have, in a way, broken the initial particle networks, and you can see that if you re-stretch the sample a second time, you have lost the initial reinforcement. So this is a kind of Moulin's effect, which you can follow by the scattering. So this is all I wanted to say about nanoparticle structure due to time. So to conclude at this stage, I would say that what is close to matter is understanding the aggregation effects, and in particular, as I'm a scatterer, I think it is interesting to know that we are more or less able to simulate the scattering and to make it in agreement with the electronic micrography. On the other hand, I think there are still some open questions which are about the scattering under deformation, the mechanism of rearrangement of the clusters, particularly trying or not trying to understanding in terms of affine deformation and non-affine deformation, and relating it to mechanical effects. So now the second part of the talk would be about not the nanoparticles, but the chain deformation. So let us first comment about the chain conformation at rest in the field matrix. So this has been now studied more than before, and it has been scattering mostly by neutron scattering. I think it's here one of the only way to get the information. And for that, people used the so-called zero average contrast method, in which you can get the form factor of the chain through a mixture of normal chains and deuterated chains, which have the same average scattering length density as the silica. So this is the so-called 3-component zero average contrast method. And you can also improve or try to attenuate the possibility, the different complication which could arising by doing more or less the same measurement, but now with 4 components, where the fourth component is a matrix made of some monomers which are non-deuterated and some regular monomer, so that you make a statistical copolymer, and this statistical copolymer is made in such a way that you completely match the signal of silica. And inside this so kind of solvent, okay, you add some deuterated chains and non-deuterated chains. This is called four components. So when you do this kind of things, you obtain the figure on the left here on the top, where you see that basically the scattering is not very different from the one without any particles on the say on the right hand part of the figure here. Meanwhile, on the left hand part of the figure, you see a strong increase compared to the 0% case. So this has been several explanations has been made, and I want to quote one of the last paper of Ch1, Jacques Gestin, and Sanat, which propose that the extra scattering at low Q is due to a spherical shell in which the balance in between the number of deuterated chains and the number of hydrogen chains is not the same as in the matrix, because some chains, the deuterated chains, for example, are more adsorbed, or the reverse. And if you take this into account, you can explain the scattering. Other ways have been done recently also by Boué, Gestin, where they extrapolate the number of deuterated chains to 0, and they conclude more or less the same. This was also concluded by Bange, Enix, and Oberdices. So altogether, there is a kind of agreement on the fact that the neutron scattering can allow to see the chain conformation at large Q, and show that it is actually not perturbed very much by the fillers. Meanwhile, at low Q, there are some complications due to the unbalance of the normal chains and the deuterated chains around the particles. And I wanted to show you this case before finishing on that. You can see here some three-component ZAC measurement of Nicolas Jouot, in which things are actually, what I wanted to show is that the behavior is not rational. When you have in the first case with some small matrix chain, you see that the scattering is actually stronger for the largest concentration of nanoparticles, which seems logical. Then, if you increase slightly on the left-hand side, but on the bottom, if you increase slightly the molecule weight of the matrix chain, you see that the 5% concentration here is sitting on top of a reference sample with no particle. Meanwhile, the 15% is actually giving a much stronger signal. Now, if you go to even larger molecular weight, you see that this is the inverse. The 5% is much more unbalanced than the 15%, and so on. So altogether, what I just wanted to say is that apparently it's not very easy to control the adsorption of the different kind of chains. It seems to be largely not under control, at least in this case. So now I want to sorry, I have a technical problem. Sorry, I will escape. I will start again. Okay. Is it okay?
Yes.
Now you can want to show the same effects, but now under stretching. So in our case at least, we stretch our sample above a glass transition, we quench it, and then we do the observation at room temperature. And we manage in such a way that we should have the form factor of a change because we are under the zero average contrast conditions. So what we observe is, first I want to make you notice that the scattering is now resembling the scattering of a normal chain. You don't have anymore this butterfly effect. And second, I want to show you several cases for the same mixture, but under different elongation ratio, 2, 4, and 6. And you can, in any case, you can compare the red symbols here, which correspond to the non-filled system, okay, and the blue symbols, which correspond to the filled system. And you have both the scattering along the perpendicular direction here, always on the right, because it corresponds to smaller slices, because it is shrunk, and so it corresponds to a larger Q, because Q is the inverse of the size. And you can see that the difference between the perpendicular and the parallel one is increasing with scattering very nicely. But what is particularly striking is that actually you don't have very much difference in between the scattering of the chain in the non-filled system and in the filled system. Of course, in the case I showed, you have a reasonably small concentration of nanoparticle, 5%. So we also did, as you can see on the right, the bottom right, we also did some much more concentrated system, but in this case we could not deform it a lot because the modulus was so high that it would break. So we only reached a value of 1.28, for which you can see again that the scattering superposed in between the non-deformed one and the deformed one. What I wanted to show here is that although the scattering are very close to each other, the initial stress during the first deformation is very different. You can see here the stress strain curve. So the blue one here corresponds to the system without any filler, and the other one here, the small red point, which is on the yellow curve, corresponds to the 15% filled system. And you can see that the stress is very different. Meanwhile, the scattering is very close. So it is as if when you increase the concentration of particles, when you increase the concentration of particles, you have a neat increase of the initial stress strain curve, but you don't have so much difference for the chains. So this led us to propose that this curve, the stress strain curves, are made more or less of two contributions. One is the contribution of the chain, which is more or less always the same. You can see here the green one, and with the different symbols, it's always all these contributions are parallel to each other. Meanwhile, at small elongation ratio, you have a very different first increase. And so if you subtract the stress strain curve of the matrix from the other stress strain curve, you obtain some rather flat contribution, which you can attribute to the formation of the clusters of the organization of the filler. Okay, so it is as if actually you had a system in which you have two contributions, the one of the untangled chains and another one which is due to the fillers and which correspond to a very strong initial stress and which you could represent as a kind of initial friction. Also, you can follow the relaxation of a chain after stretching. So here is different zero average measurement under strain at 5% concentration of fillers compared to 0% concentration of fillers. And you can see again that if you stretch your system and then let it relax with time, so that means we maintain the film at constant length above the glass condition during a very long time of about 24 hours. So the stress relaxes completely. And you can see that in both cases, whatever it is filled or not filled, the relaxation is showing more or less the same kinetics. So of course, this is a very incomplete experiment, but it would be nice to go on this direction to actually follow the dynamics, the rotation dynamics of the chains, and comparing filled and non-filled. And I would suggest that they could be very similar. So I will just show you very briefly that you can have exactly the same effect. That means no strong effect of the fillers on the chain deformation in an industrial system on the right, which was actually Michelin polymer with some aggregated silica. We also observed the same identity in between the chain with fillers and without fillers. And also in another case, magnetic nanoparticles dispersed in polystyrene, in which again you don't see much difference in between the deformed chain in presence of fillers and without fillers. Okay, so for this part, I just want to conclude that it is, I think, more or less admitted that even, unless the confinement is very strong, there is no strong effect on the chain conformation at rest. Now, I think that under deformation, there are still some open questions, in particular trying to understand better the weak difference in between the chain conformation in non-filled and filled system and how it is related to the mechanical effect. So now I have a last thing to show you, which is not really the chain conformation of inside the system, but the conformation of the grafted corona around the different nanoparticles. In the case of grafted nanoparticles, we were able to again to use this statistical copolymer matrix, which allows us to actually match the silica, so that we can only see the scattering from the corona. And this is what you can see on the right hand side here. For different patterns, for different elongation ratio from 1 to 4, and different silica concentration from 4 to 14% per volume. And so this different scattering represent the scattering only from the corona, but they contain both the form factor of a single corona and the Fourier transform of the distances between the different corona. So they are difficult to interpret, but what you can do is to use some data which have been acquired by X-rays on the left-hand side, which have been acquired from the signal of silica only, since in the same samples we are not sensitive to the difference of scattering, neutron scattering length density. So from this weird curve on the left, we can extract the structure factor of the systems. That means the Fourier transform of the distance between the silica particle. Then, knowing this, we can introduce them on the right hand side patterns, and by dividing the signal by the structure factor, we obtain the form factor of the corona, and this corresponds to this kind of curve here. You have in log-log plot here on the right and the left, you have the form factor of the deformed corona for different elongation ratio. And what you see is that this form factor is strongly deformed. So, in my opinion, this is to compare to different theories which were proposed, in which were saying that the increase in the mechanical reinforcement is due to the fact that the different nanoparticles are surrounded by a very harder polymer region, even forming some kind of bridges in between two clusters, like here. And so this would be the origin of the reinforcement. In our case here, I think at least the grafted corona are not glassy. They are strongly deformed. So that means that this contribution of the frozen part around the clusters is not always visible. At least in this case, it is not. Meanwhile, actually, we have some reinforcement. The last thing I wanted to show you is a very simple example which doesn't involve scattering. It's just directly observed by electronic microscopy. This is the case where the nanocomposites are made of very strongly phase-separated aggregate of nanoparticles. And you can see that if you deform them above CG, all these different clusters, they are strongly deformed. That means that the polymer, which is inside the nanoparticles, inside these clusters, is actually very flexible. Okay, so this is all I wanted to say. So, well, I would be happy to have some questions.
So Francois, this is very, can you hear me? François, do you?
Yes, I hear you, yes.
Okay.
Yeah.
So I really liked this last piece you showed about the form factor. And I was going to comment that there are two or three things that sort of come to mind. One thing was that we had a paper, I think, in ACS macro letters where we took nanocomposites, and I think we did startup of steady shear, and also we did large amplitude oscillatory shear. There we didn't measure the stress, but we did measure, mechanical response. And then we did transmission electron microscopy in 3 directions. And that shows how the clusters sort of reform under the action of stress.
Yeah, can
So
you
I was
speak
going to say,
louder because my computer is not very good in.
okay, I'm already screaming. I don't know how much louder I can speak.
Maybe being closer to the mic.
Okay. So my comment really was doing TEM in those cases of large deformation gives a lot of very interesting conclusions.
I think so, yes.
Yeah. So that might be useful to check.
Okay, so okay. So what do you want me to answer? I think it's true.
Nothing. I just made a comment. That's all.
Okay.
See, I have a question. The Mullins effect, is that done on, you're just doing colloidal silica, or what are the materials?
Can you say it again?
Yeah, you did the Mullins effect, the scattering with Mullins effect. Was that colloidal silica that you were working with? The stretching?
Which kind of silica am I working with?
Right.
It's always, and in this, all these examples, it's always the same silica, 10 nanometer size.
Okay.
So what is
So
exactly the question?
Yeah, I'm wondering what the difference is. I mean, a commercial fumed silica.
Oh, yeah, the commercial
silica.
one was for the what I call the industrial systems.
Yeah.
In this case, it's some rhodia-solvay silica, which is aggregated and which you try to disperse and partly disaggregate by the mechanical steering in the kind of the usual mechanical steering which is used for rubber industry. But all the other cases, when I did not say in so-called industrial systems, all the other cases are just made out of individual silica, which is aggregated during the mixing with the polymer. Does it answer your question?
Yes, it does. But usually the network, normally it's done with carbon black, right? The Mullins effect. So I'm kind of surprised that you see it with colloidal silica.
You're kind of surprised what?
I'm surprised that you see the Mullins effect colloidal silica. The single particle silica,
You're surprised that I am seeing what?
The stress effect, the Mullins effect, destruction of the network.
You mean the on the stress strain curves?
Yes.
So what do you mean by what would you be expecting?
That the particles didn't form that robust of a network, the colloidal silica, the single particle silica.
Okay. So what we observed is a very strong increase when we deform at the first time. Mm-hmm. Later on,
yeah, I saw that.
The increase is much lower because we have done a very large deformation. Because this is not like in a tire. In a tire, the deformation is not so large. But in our case, we stretch by a very high factor. Does it make things a little more clear? Just wait one moment. I just asked my colleague to connect herself on her computer because maybe her loudspeaker is working better than mine.
Yeah, this one other thing. Does anyone else have a question or that maybe?
The question.
Hey, one other thing that could you say a little bit more about the acid base with the latex system that you mentioned?
A
I
little
haven't
more
seen that
about
before.
what?
Acid base with the latex. The
You mean
latex
the
system.
mixture between the latex and the nanoparticles?
Yes, yeah. I hadn't read that before. That looks pretty interesting. You can tune the. You're saying that you can tune the the network with the acid base, the filler network.
Yeah, you mean
I think it was from '99, but yeah, I haven't seen that paper.
so you're talking about some latex and mixture of latex polymer beads and nanoparticles?
Yeah, I think it was with Ralby,
Yes.
Ralby,
Okay.
1999.
1999. Yeah.
This
Yes,
one.
that slide.
Yeah.
Yes.
Could you expound a little bit more about that? I haven't read that, but that looks pretty interesting.
Okay. Well, what Rarby did actually, so he mixed some latex beads and some silica nanoparticles, and he noticed that when you could have the same size, that means the latex beads and the silica particles were of the same size. In this case, you could obtain some very random mixing, which you can see on the left on this let me this picture, okay? And then this was when they had some basic pH, so that the latex are charged and the nanoparticles are also charged the same way. And then if you, yeah. Okay, fine. Now, owing to my colleague, I think I would hear you much better. So
Okay. Yeah.
yeah. So you're okay. So shut the fuck up. Sorry. There's a lot of. So what should I do? So the idea in this case is that you obtain the aggregation through the change of pH, which induce the changes of charges, and which induce an aggregation of nanoparticles. And so you can vary the aggregation state just by the pH. Apart from that, the system is the same. And this trick was expanded by actually Julian Oberdisser, and he actually made all of his nanocomposite like that by mixing latex nanoparticles and silica nanoparticles. Is it more clear?
Yeah. Thanks. Thank you. Yeah. I have to go back and read that, but that's pretty interesting for us. Yeah. Thank you.
So actually, in the case of Julian, they made the trick was that they mixed some normal latex nanoparticles and some deuterated latex particles. So at the beginning, the chains were not mixed, and they had to wait a certain time until the polymer chains diffuses. Actually, I see Guillaume Daiza in the attendees, so he can explain us better if he likes. Actually, this trick was rather clever, but it was imposing a first step in which the two kinds of chains must have time to mix together, and later on, the system would be very similar to a system in which you have mixed the D and the H chains in solution together with mixing the nanoparticles. Am I clear?
Yes.
Yeah. Yeah, thank you. That's pretty interesting for us. I think if there's no other questions, I think thanks for giving the presentation. I guess that
Actually, I do have a couple of questions. So I was going through my notes here. So first question regarding towards the end of your presentation, the studies on the effects of these glassy bridges. So first, I was wondering what was the smallest deformation that you used studies?
Sorry, can you repeat the question? This was about the kind of bridges in between particles due to glassy...
Yes, for the studies that you did with the glassy bridges, I was wondering what the smallest deformation you used was for those studies.
The smallest one?
Yes.
I think it's 1.5. It's an elongation ratio of 1.5, right, which is the ratio between the final length to the initial length.
Okay. I just wanted to comment.
What you mean is that there are always very large deformation?
Right. So I just wanted to comment. It would be very interesting if these studies could be done at smaller deformations to study the effects of these glassy bridges. Because some people in this field now are thinking that these glassy bridges might have some other stronger effects that occur at lower deformations, something that would be less than lambda equal to 1.2. And it would also be interesting to see how filler volume fraction could affect that. So for example, if you have more filler than the segment length that would connect the different nanoparticles together could be smaller. I think that could potentially be a very rich study as to see the effects of those layers at those small deformations.
Okay. Yes, I think you're right. It's a very good remark. It is possible that those bridges are destroyed under rather strong deformation. So yes, that's true. We could try to have a look at a much lower deformation, like 1.1 or something like that.
Yes, that would be very interesting. And I had one other question regarding the neutron scattering studies on the effect of chain alignment. And so those studies were done on polystyrene.
Yes.
And so I was wondering if you have any insight as to how this chain elongation might change if you use more rubbery polymers, something like polybutadiene, which has much lower hysteresis and will dissipate that imparted tensile stress much less readily.
Okay, so let me have a look at another transparency, which is for some dispersion of nanoparticle with say, let me find it. Okay, I will show you just now. Yeah, this one. Okay, can you see it?
Yes.
On the right hand side, you have different scattering curves, which are actually not the it is not the form factor of the chains, it is the form factor times the square of the scattering vector, q squared times S1 of q, which is so-called the Kratky plot versus q. And so it is usually showing this initial increasing part and then a plateau due to the Gaussian chain conformation. And what you can see on these curves is, again, that the system is not very different under strain and under strain with and without nanoparticles. Okay?
Okay.
And you can see that, of course, on the top, on the right, you have an increase of, and a maximum. This is the effect of the transverse deformation, which is a kind of shrinking effect, which produces this maximum here. And in the parallel direction, this is more or less the opposite. This curve is abated by the deformation. But you see that in both cases, the signal of the dark and the green symbols, which correspond to the system with and without fillers, are the same. And there is a slight difference with the blue system, which corresponds to a stronger, a larger concentration. But this difference is more or less the same for isotropic state, deformed state, and so on. So altogether, we don't see much deformation, even in this case, which is closer to what you said, because it's the matrix is starring butadiene rubber.
Right.
Which a part of this matrix is made out of deuterated chains, and the fillers is diasolvay aggregated silica.
All right. And just one last thing: has any similar study been done, but with using grafted chains?
Yes, this has been. You mean silica with butadiene grafted chains?
Right. Looking at the chain conformation under deformation, the effect of grafting specifically.
What polymer are you talking about? Isoprene, polyisoprene?
I mean any sort of elastomer. I'm just curious if people have done these studies on the chain conformation. In the case when it's grafted and also under deformation.
Okay. Well, I would dream to do it, but I did not. We did not. The reason is mostly that we must, in this case, get rid of the signal of the corona. And to do that, we need to graft some chains, which would be some mixture of normal and deuterated monomer, so that they would not be distinguishable from the matrix one. And so then, in this case, we could do some zero average contrast by putting, in addition to that, some normal and deuterated chains. You understand what I mean? We have to get rid of the corona. So this is why I think no one did it, as far as I know. Okay. But that would be nice to do. I was actually thinking of it yesterday evening. Thank you.
Thank you.
François, can you hear me?
Yes.
I just have a question on the friction. You spoke about friction between the fillers a bit later in your talk.
Yeah, maybe I can show you. You mean this?
Yes, exactly. So what do you expect if we can change somehow the coefficient of friction of the aggregates? What would you expect on the chain conformation? Like, for example, if you put some magic powder that can reduce the friction of between the fillers,
Yes.
and you stretch in the same way. So basically, you change one of the two springs that well, it's not really a spring. It's like I don't know how you call this, the plastic element.
Yes.
So the chain is the spring, is the Maxwell element,
Yes.
and the pink one is entanglement.
Yeah.
What is the pink one?
It's a friction in between chains. It's a relaxation. It's a rotation.
So it's purely viscous.
Yeah, it's purely viscous. Yes. Yeah, it's
Okay.
a classical Maxwell element. What is added is the friction contribution due to the fillers. But in principle, the part which is on the right here would be the same whatever the filler concentration.
Yes, this okay. So when you stretch, then you see, yeah, at least you think that you have bigger radius of gyration for the chains because they get stretched,
Yes.
and this comes at a particular threshold when the aggregates start to move relatively, right, from each other.
Well, in principle, the very naive picture, very oversimplified picture is that this part is always the same. So the way the chains are deformed is always the same, whatever this friction part is here. So this is completely, the deformation of a chain is completely disconnected from this filler contribution.
Okay.
This was the idea. It's very naive, but it's supported by the fact that you get the impression on this curve here that this contribution, which is the contribution of a chain only at 0% fraction, is always the same for the different filler concentration. So that if you subtract this curve, 0% curve, from all the other one, you obtain always some very flat rest. The rest of the subtraction doesn't vary with the elongation. It stays constant.
At big enough elongation. If you look at the beginning, then you see a difference, right?
Yeah, you have to wait until 1.2.
If you're in the linear regime that you don't have any pain effect, then okay, everything is elastic, and so there is a difference. And then as soon as you break somehow you reach the threshold of the aggregates, like they become purely plastic and they flow in the polymer melt, right? That's the idea.
Yes, but there is still some friction in between them.
Yes, and okay, so that's exactly my point. And now, what if you can change the friction between them? What if you can tune this level of friction between them? What do you expect for the chain conformation? So from what you say, it's like the same.
Exactly the same.
Exactly the same. Okay. Well, okay, with the aggregate swimming happily in the melt of polymers, and so
yes.
you don't change anything on the chains.
Like
okay,
when you have individual silica particle, the aggregates, they swim happily in the system and you don't see any reinforcement.
Okay.
This is very simplistic.
Now, from what you show, indeed, it looks like okay, it doesn't play any role. So it's like there is no particular attraction between the polymer and the silica and the filler in this case. So they don't care. I mean, the chain doesn't care. Chain don't care if the aggregates are
Yes.
away from each other somehow.
Yeah. It is as if there were no interactions in between the chains and the fillers.
And this would be very interesting actually on kind of attractive nanocomposites above the glass transition. For example, if you take this P2VP above the glass transition and you do this kind of tests, because now the polymer and the silica like each other, then we may see the stretch of the chain during elongation.
Yes.
And this, from what you say, it has never been done.
I don't think so. I don't know.
Like if you take partly deuterated P2VP to have zero average contrast on the silica, you go above the glass transition and you do a tensile test, then in principle you should see something.
Okay.
Very, I mean, I think, yes, very clearly you should see a big effect because you have strong attraction between the polymer and the particles.
D'accord.
And in this particular case, then we should see something. That I think that would be a beautiful experiment.
Okay.
Or polyvinyl alcohol also, or all this kind of polymer,
Wait, yes, I see.
which strongly interact with the silica.
With the silica surface.
Yes. Well, the only condition is to be above the glass transition. For P2VP, it's 100 degrees, so I think it's feasible, let's say, without any big machine.
Yes.
You need to be able to heat up and stretch at the same time. I think it's feasible.
Okay. I don't know how many of us are still there. I think there are only two. You and me.
No,
we're still here.
No?
I think.
Yeah, well, 4 at least. Yeah.
Okay. Yeah, sure. My photo array is not very good. Okay, so do you have other questions or whatever?
Can you send the slides maybe?
Yes, I will. Actually, I think I will put them on the. I can send them, but I want to put them on the repository of the APS also.
Yes. Thank you.
Welcome.
Thank you, Francois. It was a wonderful lecture. Appreciate it very much.
Yeah, thanks. I guess we can sign off then.
Yep.
So what time is the Asian one, Francois? You're going to redo this talk.
The Asian conference is actually it's too early for the States because I think it's 5 a.m. in Eastern Standard Time.
Oh, okay,
And
right.
it will be, I think it will be 6 p.m. in Beijing and 7 p.m. in Tokyo.
Okay, all right. So I'll try to send a notice at least to some of the people over there.
Okay, yeah, thank you very much. Yeah, because they did not answer, they did not react.
Yeah, right. So at least we should get some response in advance. It's tomorrow, so it'll be tomorrow, right?
Yes, it will be on Friday, so it will be tomorrow. Yeah. So
Okay.
for them, it
All right.
will be tomorrow evening.
Okay. All right. I'll try to send an email and see if they're going to. See,
Yeah,
actually,
thanks.
we could try to do the same thing with the. There was a Japanese invited speaker, so try to get the same thing. But, yeah, thanks for putting in the effort to do this. It's really useful. Interesting.
Welcome.
Yeah.
At least
Right.
it's a little less frustrating.
Yeah. Well, we stayed healthy at least, so some bright side.
Yeah.
Okay, well, have a good night.
Thank you very much.
Thank you,
Thank
François.
you, everyone. And I send
See you
you
next.
the slides.
Thank you very much. See you next time.
Thanks.
See you next time. Bye. Bye-bye. I let you quit. Tu vois encore le truc, toi, parce que moi, c'était trop petit. Ah, ça y est, là. Presque. Alors, comme ça. Hello, Sanat. Can't hear you. I think your microphone is mute.
It was mute, yes. Can you hear me now?
Yes.
Okay. So I think this is beautiful stuff.
Thank you.
What I was thinking is that I will send you this paper where we did the large amplitude oscillatory shear.
Yes, okay.
But this is polystyrene, graph silica, and polystyrene about TG. And basically the clusters break up
Okay.
as you deform. That's one thing.
So you can see them by electronic microscopy?
Yeah. It's very, very dramatic. That was one thing. The other thing which we sort of made a statement, that the mechanical reinforcement in these systems is basically carried by the particles.
Yes. This is what I believe. Yeah.
Yeah. So this statement you made that the matrix chain seems to be irrelevant is completely consistent, but your scattering evidence is different from, so mine was just a conjecture.
Okay.
You show that the conformation doesn't change, which is actually beautiful, because that tells you that really everything comes from particle restructuring.
Yeah.
And so if you would take a perspective, then for things like the Mullins effect, for all those things, this is idea that it's particle networking that dominates the physics, right?
Yes.
That's been sort of proposed. So I think you're sort of coming back and reinforcing that viewpoint. Both the Payne effect and the Mullins effect are all coming from particles, and that's all.
Mm-hmm.
So I think you can make that big statement. I think that's the bigger message from your whole thing.
Okay. I don't know exactly. I do not know exactly what we already published. So
Okay.
probably it was not so clearly stated.
Right. I think that the data that you showed today, when you look at it together, really supports a much bigger picture. And so, it might be worth saying that, in a short note.
Yeah.
Especially now that, you do this, especially when you do the deformation on these grafted particle systems. And you show that, I think that was also very nice right at the end where you show the particle clusters sort of expanding or changing shape under the action of stress. I think Didier Long doesn't like that picture, but that's, I think, the real truth of the whole story.
Mm-hmm.
Yeah.
I think the remark of the student about the fact that probably things are different at very small deformations is probably true.
Right.
But as soon as you increase slightly the deformation, then we go into the schema I showed.
Right. Anyway, so I should go. I have to go teach in 2 minutes.
Okay.
But thank you for doing this.
You're welcome.
All right.
Hope
We
to
will
see
talk
you
soon.
sometime.
Absolutely. And I'll send you a couple of papers for you to look at.
Okay.
All right. See you, François.
See you. Bye.
Bye.